In this question, a fictional scientist is investigating a reversible reaction involving fictional substances A, ET3, AET2, and T2 at a temperature of 391 Kelvin and a pressure of 1 atm. We're given the equation, including that reversible arrow showing our reaction can happen forwards and backwards. We're also given K, the equilibrium constant for this equation, is 0.411. Okay, so our goal in this question is going to be finding an expression for the reaction quotient Q for this reaction. We're then going to be calculating the reaction quotient Q at the start of the experiment and using that to figure out which direction our reaction is going to proceed. So let's head to the reference sheet. Here is the reaction quotient, and you can see the equation looks identical to that for the equilibrium constant. Again, we have our expression for Q involves the concentrations of our products, which are C and D, to the power of the coefficients in the numerator of our fraction. And then in the denominator, we have the concentrations of our reactants, A and B, to the power of their coefficients. Again, we're told only gases and solutions are included in the equation. So this is exactly the same as the equation for equilibrium constant. The difference is that the equilibrium constant only applies at equilibrium, whereas the reaction quotient can be calculated at any moment in a reaction and can be used to tell us where we are in our reaction and which direction we're going to be proceeding in order to get to equilibrium. So we're going to be writing our expression for the reaction quotient exactly the same method as we used for finding the equilibrium constant expression. So in our numerator of our fraction, we've got our products. So in the products, we've got AET2. It's in solid form. Since it's in solid form, it's not going to appear in our equation because to appear in our equation, we need it to be gas or solution. Next, we have T2. That is in gas form, so that is going to appear in our equation. So we've got the concentration of T2, and it's going to be to the power of its coefficient. There's just one of it in the equation, so it will be to the power of 1. But remember, to the power of 1 is just the same as the thing itself. So that's it for our numerator. Then in our denominator, we've got A, which is a gas. That's great. That means we can include it in our equation. So we've got the concentration of A, and that's going to be to the power of its coefficient, which is 2. So we're going to have concentration of A squared multiplied by our other reactant, which is ET3. That's a gas. So again, that can be shown in our equation. So we've got the concentration of ET3, and it's got a coefficient of 2, meaning it's going to be to the power of 2. So that's going to be our reaction quotient expression. So let's fill that in here. We've got T2 on its own. We've got A squared and ET3 squared. There we are. Awesome. So there's our expression for the reaction quotient. We're then told at the start of the experiment the concentration of A is 1.75 molar, the concentration of ET3 is 1.20 molar, and the concentration of T2 is 0.868 molar. So we need to go ahead and calculate at the start of the experiment what is the reaction quotient Q. So we're just going to go ahead and put in all our concentrations from the start of the experiment into our equation. So the concentration of T2 is 0.868 molar. Then we've got the concentration of A, which is 1.75, and that's squared, multiplied by the concentration of ET3, which is 1.20, that's also squared. So if we put that into our calculator, we're going to get a value for Q of 0.197. So we can fill that in down here. Q again doesn't have any units, so we can add a note about that here. There's no units for Q or K. Okay, awesome. So we've done the hard work now. We got our expression for Q. We've calculated Q. Finally, we need to figure out what's going on in our experiment using those values. So for K, we had 0.411 given to us in the question. For Q, we had 0.197 that we just calculated. So 0.197 is less than 0.411. So Q is less than K at the start of the experiment. So we can fill that in here. Q is less than K. So which direction will the reaction proceed? So if Q is less than K, we need Q to get bigger. In order for Q to get bigger, we're going to need the numerator of our reaction to get bigger and the denominator to get smaller. So we're going to need to increase our concentration of T2 and decrease our concentration of A and ET3. To do that, we need our reaction to proceed in the forwards direction so that we're converting A and ET3 into T2. That's going to make our Q bigger, and our Q is going to get bigger until it equals K, and then we'll be at equilibrium. So which direction will our reaction proceed? It's going to proceed in the forwards direction towards the products because Q is less than K. So these questions look really similar to the equilibrium constant questions we've already done. Finding the expression for the reaction quotient is exactly the same as finding the expression for the equilibrium constant. Then substituting in our numbers again is the same process, but for Q, or the reaction quotient, we can use numbers from any moment in our experiment. It doesn't have to be equilibrium. So we're using our values from the start of the experiment to figure out what was Q at the start of the experiment. Finally, we're comparing Q and K to decide which direction will the reaction proceed. If Q is less than K, it's going to proceed forwards towards the products. If Q is greater than K, it's going to proceed backwards towards the reactants.